Too far bottom left. All right. A JC matrix is given from directional graph is shown, right? So P doesn't go to P. P doesn't. The only thing P goes to is S. So I'm going to draw a P to S, which is already drawn. Okay, that's done. And it doesn't go to P. Then we're going to go to Q. Q goes to P. Where's Q to P? Q to P is 1. Okay. And then R, Q goes to R. Okay, and that's that one there. Q goes to R, and then the rest of the zeros. R doesn't go to anybody but S. R goes to S in one direction. Okay, T doesn't, R does not go to T, done. S is, yeah. Now, S to T, this way. And then T goes to Q. Is it just T to Q? Anybody get that? As their sort of their diagram for it. It's question 6, isn't it? Yeah, I got book got the same answer. We're all good. Okay. Now, how many walks of length 2 are there from Q to S? Q to S will be here to here. What do you think the answer is? 2. And we also have to write them down. So we have to write down what way we're going to organize this. So how do we go from Q to S, lads? Can anybody tell me? In a distance of 2. Q, R, S. And that's actually the answer it gives you in the solutions. It just says write down Q, R, S. So Q, R, S is one of them. What's the other one? Where's QPS? Does P go to S? Oh, it does. QPS, yeah. Q to P to S. Is that right? QPS is the other one. QRS and QPS. Okay. How many walks of length 3 are there from T to S? Now, where's T to S? Length 3 would be A cubed. T going to S, there'd be 2 of them. Now, let's write down the ones going from T to S of length 3. Okay, T, 1, 2, 3. What's that one? TQRS. Ever see that? TQRS. Okay, that's one of them. What's the other one of length 3? Anybody else have another idea? TQPS. Okay, let's find out. TQPS. Yeah, that'll do the trick. TQPS for the other one. TQPS. Okay. Ave says that at least one walk of length 4 from each fair to say back to itself. Is she correct? If so, write down one walk of length 4 from each fair to say back together. Are all of these cycles? Okay. So P to P has 1, Q to Q has 2, R to R has 1, S to S has 2, and T to T has 2. So yes, there are walks that link it back to itself. Did we see the main diagonal there? That's what I'm shading in there. How often does it go back to itself? Okay. And what it wants me to do is it wants me to do 1 for each one. And I reckon they're probably all going to be cycles. Okay. Anybody care to write down P back to P? Anybody? How'd you do that? P back to P. P, PS, T, PST, what's it? Q, and P. Yeah, I'll take that. Is it a cycle? Yeah. Okay. There we go. What was the last 2 letters again? QP. Okay. I've done P to P. Now I'm going to do Q to Q. That's an easy one, isn't it? QR S, T, Q. See that there? Okay, what about S to S? It's the same thing, isn't it? Except it's in a different order. It's S, T, Q, R, S. Okay. R to R is easy as well, isn't it? It's just the same stuff over and over again. And what's the last one we have to do? T to T, which is exactly the same thing, except we're just going to go T, Q, R, S, T. Yeah, we got one of each type. Perfect. Okay, they're all cycles. Okay, and that's that one done. Is there a part 5? Is there a part 5? Did I put on the next page? Oh. Would you all agree that it says you want to do a walk from every vertex to every other vertex? Is it correct? Now look at this. What we're going to do is we're going to write down when are the parts not equal to 0, right? So do you see this location here? Do you see P to P? Yeah? Where is it represented? It's represented by a walk of level 4. Agreed? Where is P to Q represented? A walk of level 3. Do you get what I'm saying? Where's the next one? Where's P to R represented? Walk of level 4. So what they're saying is that if you add all the matrices together, what you find is there'll be no zeros left. Every single one of them has, every single spot has, so in the all 4 matrices listed, if I click any of these points, see this point here, the one I highlighted in yellow. If you go down to the other matrices, I guarantee you'll find a non-zero place where it's not 0. You'll find a place where it's not 0. That means it actually contains a walk. Does that make sense? So what I'm saying is that every single location in the matrix is represented by a non-zero entry for all 4 matrices, and that means they all have a walk from any point to any other point. So if you just go through them all, you'll find that all of them will always have something that's not 0. So take this one as an example. When is it not 0? Nope. There it is right there. It has a walk of length 3 from R to Q. That makes sense? Now try to word an answer like this is the real test here, right? So I think what we'll say is that look at all 4 matrices, each position by a non-zero entry at least once in the first 4 matrices. Done. I like that way of explaining it.